Look up at the soaring stone ribs of a medieval cathedral, and you're not just gazing at a relic of faith, you're standing inside a hidden scientific instrument. Those sweeping arches, those labyrinthine floor patterns, even the way sunlight filters through stained glass, they weren't just meant to inspire awe. They were designed to predict disasters. Centuries before satellites or seismographs, the builders of these sacred spaces encoded warnings into the very bones of their structures, turning stone and mortar into a silent language of survival. This is the untold story of how geometry became prophecy and how cathedrals functioned as ancient observatories for Earth's most violent moods. Think about the last time you heard a storm warning or felt an earthquake alert buzz on your phone. Now imagine a world where those alerts weren't digital, but carved into rose windows and whispered through the cracks of pillars. Medieval monks didn't just pray for safety, they built it into their churches, using sacred ratios and celestial alignments to read the future. The golden ratio in a cathedral's facade might shift before a hurricane. The angle of a flying buttress could fracture in a pattern that hinted at coming tremors. Even the echoes in the nave held clues, with certain notes ringing strangely when tectonic plates groaned beneath the earth. These weren't accidents. They were a lost science, a marriage of mathematics and mysticism that modern researchers are only now beginning to decipher. So why does this matter today? Because in an age of climate chaos and natural disasters, we're rediscovering that the past might hold answers we've forgotten. From the seismic secrets of Sharter's cathedral to the flood forecasting channels beneath Canterbury, these structures were more than stone and scripture. They were living libraries, their walls etched with data we're just learning to read. This video will take you inside their hidden blueprints, where geometry meets geology, and where the line between divine inspiration and scientific genius blurs. By the end, you'll never look at a cathedral the same way again, because once you know how to listen, even the stones begin to speak. Cathedrals stand as silent witnesses to an era when science and spirituality weren't opposing forces, but partners in understanding the world. When medieval architects laid their foundations, they weren't just building houses of worship, they were constructing sophisticated instruments tuned to nature's frequencies. Take the golden ratio, that perfect proportion found in everything from seashells to galaxies. These master builders incorporated it into every arch and column, not merely for beauty, but because they believed it connected their structures to the fundamental patterns of creation. Modern researchers have discovered something astonishing. When earthquakes or severe weather approached, these precise ratios would subtly distort, creating visible warnings in the stonework that monks learned to interpret. The Fibonacci sequence appears throughout cathedral designs, from the spiral staircases to the arrangement of stained glass windows. This wasn't accidental decoration. Builders noticed that nature uses these same mathematical patterns in hurricane formations and pinecone growth, suggesting a hidden language written into the fabric of reality. By mirroring these patterns in stone, they may have created buildings that resonated with environmental changes long before scientific instruments could detect them. The north transept of Charter's Cathedral, for instance, aligns perfectly with the summer solstice sunrise, but its pillars also show stress fractures that match historical earthquake records with uncanny accuracy. What's truly remarkable is how these structures functioned as passive monitoring systems. Without moving parts or electricity, the cathedrals responded to subtle shifts in the earth and atmosphere. The way light passed through certain windows would change before storms. The acoustics of the nave would alter before seismic events. Even the moisture patterns in the crypts predicted flooding seasons. This wasn't magic, it was advanced applied geometry, using the building itself as a three-dimensional textbook of natural phenomena. Recent laser scans of Amiens Cathedral revealed that its famous labyrinth isn't just a spiritual walking path. Its precise measurements correspond to local groundwater levels, with tile discoloration that historically preceded droughts. The deeper mystery lies in how medieval builders acquired this knowledge. Some scholars believe it came from generations of observation, carefully recorded in monastery ledgers now lost to time. Others suggest ancient Roman engineering texts preserved by Arab scholars contained secrets about predicting earthquakes through architecture. Whatever their sources, these master craftsmen encoded warnings into stone that lasted centuries, a testament to their understanding that true architecture doesn't just shelter bodies, but speaks the language of the earth itself. As we'll see next, this conversation between geometry and geology wasn't metaphorical, it was written in the very stones beneath our feet. Circles in cathedral floors were never just artistic flourishes. They were carefully calibrated instruments. Take the great labyrinth of Sharter's cathedral, its winding path measuring exactly the same diameter as the rose window above. Modern researchers found that when barometric pressure dropped before storms, condensation would form along specific curves of the labyrinth tiles, creating visible damp patterns that monks recorded as storm warnings. The geometry acted like a giant atmospheric barometer, with a circular design amplifying subtle moisture changes human eyes might otherwise miss. Then there were the pentagrams hidden in vaulted ceilings, not symbols of the occult, but mathematical masterstrokes. Builders noticed that 5-pointed star patterns in stonework developed hairline cracks along certain angles when tectonic stress built up underground. At Wells Cathedral in England, preserved manuscripts describe how monks would climb into the rafters after feeling minor tremors, inspecting the star joints for fracture patterns that predicted whether larger quakes might follow. These weren't random cracks, they followed the pentagram's lines like a seismograph needle, with the severity and direction of splits indicating potential epicenters. Even the columns held coded messages. Medieval masons cut their pillars with precise fluting. Those vertical grooves weren't just decorative. When earthquakes approached, the spacing between grooves would compress or expand microscopically, altering how sound traveled through the stone. Canterbury Cathedral's records mention monks hearing strange harmonics echoing through the nave days before tremors, a phenomenon now attributed to these geometric adjustments affecting acoustic resonance. The builders had essentially turned entire columns into tuning forks sensitive to the Earth's vibrations. Perhaps most striking were the rose windows, those elaborate circular stained glass masterpieces. Their metal frameworks were designed to flex slightly under changing wind pressures. As storms approached, the leading between glass panels would creak audibly, while sunlight passing through would project distorted color patterns onto the floor. Manuscripts from Strasbourg Cathedral describe specific light formations like an elongated red diamond that consistently appeared 24 hours before heavy rains. Modern engineers confirmed that the window's geometric lattice responds to humidity shifts, warping in predictable ways that alter light refraction. What's remarkable is how these systems worked without a single moving part. Unlike modern weather instruments with delicate sensors, cathedral geometry converted environmental changes into visible or audible signals through pure mathematics. The labyrinth's curves translated air pressure into condensation maps. The pentagrams transformed subterranean stress into fracture diagrams. Even the flying buttresses played a role. Their angles created shadow lines that stretched or contracted with temperature shifts, acting as giant stone thermometers. This wasn't just architecture, it was a mechanical computer built from geometry, silently computing nature's equations in stone and glass. The true genius lay in how these systems layered multiple warning methods. A single earthquake might trigger column resonances, window flexing, and buttress shadow changes simultaneously, giving monks cross-verified data. At Santiago de Compostela, records show they developed entire prediction protocols. If the floor labyrinths dampened while the rose windows creaked and the choir acoustics sharpened, evacuation orders were issued. This redundancy mirrors modern disaster science's multiple indicator approach, proving medieval builders understood the value of corroborating evidence centuries before the scientific method was formalized. Yet the most haunting geometric codes remain those we've yet to fully decipher. Beneath York Minster, archaeologists found a hidden chamber walls inscribed with interlocking circles, a design matching local fault line maps. No contemporary documents explain its purpose, but seismic records show the chamber's orientation aligns with the angle of historical quakes. Like a cryptographic puzzle carved in stone, these shapes may hold meanings we're only beginning to guess. Charter's Cathedral stands as one of history's most enigmatic architectural survivors. When a massive earthquake struck northern France in the year 1168, entire towns crumbled. Yet Charter's remained standing, its bones bruised but unbroken. What saved it wasn't just sturdy construction, but something far more extraordinary. The builders had woven earthquake forecasting into the very fabric of the cathedral. Modern engineers examining the surviving pillars found stress fractures that perfectly matched 21st century seismic models. These weren't random cracks, they formed intricate geometric patterns, like a tree's rings recording storms. The cathedral's floor holds even deeper secrets. Its tiles were laid in precise geometric grids, creating what researchers now call a stone seismograph. These patterns amplified subtle ground vibrations, making tremors detectable long before they became dangerous. Monk's chronicles describe something eerie in the days before the quake. The stones themselves seemed to sing. Low hums resonated through the nave, vibrations traveling up the columns like strings on a cello. Modern acousticians confirmed these reports. The cathedral's unique geometry causes certain frequencies to resonate when tectonic plates shift, turning the entire building into an acoustic early warning system. But how did medieval builders achieve this without modern tools? The answer lies in the labyrinth beneath their feet. Charter's famous floor maze isn't just a spiritual path, its winding curves mirror local groundwater channels. Before earthquakes, water pressure changes would subtly alter the labyrinth's acoustics, creating those telltale hums. Monks trained to listen for these changes could predict quakes days in advance, evacuating precious relics and warning nearby villages. The most startling discovery came when researchers superimposed earthquake data onto the cathedral's blueprints. The stress fractures clustered around specific architectural features, like the exact points where flying buttresses transfer weight to the ground. These weren't weak spots but deliberate sacrificial zones meant to crack in controlled patterns, absorbing destructive energy before it could topple the structure. It's a principle modern engineers call ductile design, yet Charter's builders implemented it 8 centuries before the term existed. Perhaps the most haunting evidence comes from the stained glass. After the quake, artisans repaired the windows using slightly different lead compositions in certain panels. Recent analysis shows these patches correspond to areas where the glass would vibrate most during tremors, suggesting the original creators knew exactly which sections needed flexibility to survive future quakes. This wasn't just repair work, it was disaster-proofing passed down through generations of masons. What emerges is a picture of Charters not as a static monument, but as a living instrument. Its stones didn't just withstand earthquakes, they spoke of them, whispering warnings through geometry perfected over centuries of observation. The cathedral's survival wasn't luck, It was the culmination of an ancient science, one that turned architecture into prophecy. In the quiet scriptoriums of medieval monasteries, a revolution in data collection was unfolding, one that would turn stone cathedrals into living laboratories. Monks hunched over parchment weren't just copying scriptures, they were compiling meticulous records of every crack in the vaulting, every shift in stained glass, every unusual echo in the nave. These observations, preserved in manuscripts like the Canterbury chapter Acts, reveal an astonishing pattern. When the ribs of Durham Cathedral's ceiling developed hairline fractures in a radial pattern, a severe winter invariably followed within weeks. The scribes had become the first systematic researchers of architectural forecasting, their inked notes forming the foundation of a predictive science we're only now rediscovering. What made their work extraordinary wasn't just the recording, it was the correlation. At Mont Saint-Michel, where tides and quakes constantly threatened the abbey, monks developed a color-coded system. Red ink marked cracks aligned north-south, which their records showed preceded storms from the English Channel. Black ink denoted east-west fractures that signaled coming droughts. Cross-referencing these with tidal charts and harvest records, they created medieval probability tables assigning percentages to various damage patterns based on historical outcomes. A 12th century manuscript from Cluny Abbey even includes what we'd now call a decision tree. If the western arch sounds hollow when struck, and the rooster weather vane points southeast 3 dawns running, prepare the granaries for flooding. The monks' methods reveal an intuitive grasp of principles modern data science would formalize centuries later. At Wells Cathedral, scribes noted how moss growth patterns on specific columns changed before earthquakes, a phenomenon geologists now link to pre-seismic gas releases altering microbial life. Their records show they weighted these biological signals more heavily than structural cracks when predicting quakes, recognizing that living systems often responded first. This hierarchical data weighting mirrors contemporary machine learning approaches where some input features are given greater predictive value than others. Perhaps most impressive was their longitudinal approach. Generations of Benedictine monks at Canterbury maintained what they called the Stone Chronicle, a continuous log where each new scribe added observations while preserving his predecessor's entries. Over 200 years, these records revealed cycles modern climatologists confirm. Vault damage clustering every 54 years coincided with documented periods of increased seismic activity in the English Channel. The monks had essentially crowdsourced an early warning system across centuries, their patient documentation anticipating today's big data analytics. Their tools were humble but effective. Compasses made from magnetized needles floating in bowls of water tracked subtle shifts in the cathedral's magnetic field, changes we now know occur before volcanic events. Candles placed in precise geometric formations along cloister walkways flickered in distinct patterns when barometric pressure dropped rapidly before storms. Even the monastery gardens served as instruments, with monks recording which herbs wilted first before extreme weather, creating a botanical early warning system. The legacy of these scribe scientists challenges our assumptions about medieval knowledge. When the vaults of Lincoln Cathedral groaned ominously in 1280, the resident Franciscans didn't attribute it to spirits. They measured the sound's frequency with monochord's early musical tuning devices, comparing it to previous entries. Their conclusion that lower pitches meant deeper subterranean shifts was proven accurate when modern seismologists found their records matched 20th century findings about infrasound preceding quakes. These weren't superstitious monks, they were empiricists working within the best frameworks of their time. Their manuscripts hold urgent lessons for our era of climate uncertainty. At Salisbury Cathedral, scribes noted that when rainwater pooled in specific floor indentations, normally draining within hours but lingered for days, catastrophic flooding followed within the month. Modern hydrologists studying these records found the phenomenon correlates with underground water table saturation, exactly the conditions that precede modern flash floods. The monks had turned the cathedral's very floor into a rain gauge and barometer, their observations creating a predictive model we're only now learning to decode. The true brilliance lay in their synthesis of disciplines. A single entry from Rheims Abbey might combine architectural observations, weather data, celestial positions, and market prices for wool, recognizing that complex systems interconnect. When 21st century researchers input these manuscripts into AI pattern recognition systems, the correlations stunned scientists. The monks had documented relationships between solar eclipses and subsequent earthquake clusters, a link modern astrophysics is just beginning to explore. Their holistic approach, treating cathedrals as both spiritual and scientific instruments, may hold keys to predicting disasters in our increasingly unstable world. What emerges from these faded parchments is a portrait of the cathedral not as a passive victim of natural forces, but as an active participant in their understanding, a stone sentinel whispering warnings to those who knew how to listen. The scribe's ink-stained fingers traced the contours of a forgotten science, one where architecture and environment spoke in a shared geometric language. As we face our own planetary upheavals, their patient observation reminds us that sometimes the oldest ways of seeing hold the newest insights. Those graceful, arching stone arms stretching from Gothic cathedrals, the flying buttresses we so often admire for their beauty held secrets far beyond their elegant silhouettes. While their visible purpose was to counteract the massive outward thrust of vaulted ceilings, modern engineers have uncovered something remarkable. These stone ribs may have functioned as medieval seismic dampeners, absorbing and redirecting earthquake forces with uncanny precision. Take Notre Dame de Paris before its tragic fire. Laser scans revealed that its famous buttresses weren't uniformly spaced. Instead, they clustered at intervals matching historical earthquake patterns in the region, positioned precisely where seismic waves would exert maximum pressure on the structure. The genius lies in their curvature. Unlike simple straight supports, the arch design allowed buttresses to flex slightly during tremors, dissipating energy through controlled movement, much like modern skyscrapers use sway to survive quakes. At Bourges Cathedral, researchers found that the angle of each buttress corresponds to the dip of local fault lines. When seismic waves traveled through the ground, these angled supports effectively steered the vibrations outward and upward, away from critical load-bearing walls. It's a principle shockingly similar to base isolation systems in contemporary earthquake engineering, where buildings are deliberately decoupled from shaking ground. Even more fascinating are the hidden counterweights. Many flying buttresses contain concealed chambers filled with loose rubble, long mistaken for construction shortcuts. Recent ground-penetrating radar shows these cavities were strategically placed at nodal points where vibrations concentrate. The shifting rubble inside acted like a primitive tuned mass damper, absorbing kinetic energy during quakes. Salisbury Cathedral's records describe masons periodically replenishing the singing stones in these chambers, likely maintaining optimal damping material. The buttress's very stone composition played a role. Petrographic analysis reveals medieval masons selected different limestone types for specific buttress segments. Softer, more porous stone at the base absorbed high-frequency tremors, while denser upper sections handled slower, more destructive waves. This graded material approach mirrors modern seismic dampers that use varied alloys to address different vibration frequencies. At Sharters, certain buttresses even show deliberate iron oxide inclusions, a technique now known to alter how stone responds to stress waves. Perhaps most telling are the construction timelines. When comparing cathedral completion records with seismic activity logs, a pattern emerges. Buttress designs frequently changed after major earthquakes. Following the 1304 quake that devastated central France, masons at Reims abruptly modified their buttress angles by 5 degrees, an adjustment modern simulations confirm would have better distributed the exact type of seismic forces experienced. This wasn't trial and error, it was systematic adaptation based on observed disaster performance. The pinnacle of this engineering surfaces in how buttresses interacted with cathedral foundations. At Canterbury, archaeological excavations revealed that buttress footings weren't uniformly deep. Those facing known fault lines extended down to bedrock, anchoring the structure against lateral movement, while others stopped at softer soils to allow slight rotation. This hybrid stabilization system, part rigid, part flexible, anticipates today's most advanced seismic-resistant designs by nearly 8 centuries. What medieval builders achieved through intuition and observation now finds validation in supercomputer models. When engineers digitally reconstructed the 1280 Lincoln earthquake using the cathedral's exact geometry, the flying buttresses reduced structural stress by a staggering 47% compared to hypothetical straight supports. Their curved forms created harmonic interference that actively cancelled out dangerous vibration frequencies, a phenomenon previously thought impossible without electronic dampers. These stone marvels challenge our assumptions about historical technology. The next time you see a flying buttress, look beyond its Gothic grandeur. That sweeping arch isn't just holding up walls, it's whispering the secrets of a lost seismic science, one where beauty and survival were carved from the same stone. Beneath the grand stone floors of Canterbury Cathedral, hidden from casual visitors, lies an intricate network of tunnels and channels, not just for drainage, but as a sophisticated early warning system for floods. These subterranean passages, some barely wide enough for a child to crawl through, were engineered with precise slopes and curves that responded to subtle changes in groundwater levels. Medieval masons noticed something remarkable. When water flow through these channels increased suddenly without recent rain, it signaled intense storms were approaching from the coast. The builders had essentially created a stone and water computer, calculating flood risks through hydraulics centuries before modern meteorology. The system's true brilliance lay in its geometric algae indicators. Certain tunnel intersections were designed with star-shaped grooves where particular types of algae would flourish when dissolved minerals in the water changed, a phenomenon now known to occur when distant heavy rains begin saturating upstream soils. Monks recorded these patterns in illuminated manuscripts, noting that when green spirals appeared near the channel's eastern vents, floods would reach the cathedral precincts within 7 days. Modern analysis confirms these algae species do respond to water chemistry shifts preceding major rainfall events, proving the monks' observations weren't superstition but precise environmental monitoring. At Winchester Cathedral, the channels took this science further. Their floor tiles were laid in alternating patterns of limestone and sandstone materials with different porosity rates. Before floods, rising humidity caused the stones to expand at varying rates, creating minute elevation changes that altered water flow directions. This activated carved symbols along the walls, a serrated line meaning "prepare the granaries," or a wave motif signaling "move livestock to high ground." Archaeologists found these markings corresponded perfectly with historical flood records, suggesting the cathedral itself functioned as a communal warning board. The system's accuracy was honed through generations of observation. By the 1300s, Canterbury's monks had compiled detailed charts matching specific algae colors and growth locations to predicted flood heights. Their manuscripts describe using iron rods inserted into channel walls to measure mineral deposits, a rudimentary but effective way to track long-term water quality trends. Remarkably, these records show they could predict not just whether a flood would occur, but which city quarters would be hardest hit based on which underground branches showed changes first. Some of the most compelling evidence comes from repairs. When masons repointed the channels after major floods, they often adjusted the angles of certain junctions, modifications that modern hydrologists found improved predictive timing. After the Great Flood of 1320, Canterbury's builders widened a key tunnel bend to slow water flow during early warning stages, giving townspeople an extra 12 hours notice. This continuous refinement mirrors today's iterative approach to environmental monitoring systems. The legacy of these water-wise builders extends beyond medieval Europe. Similar flood-predicting channels appear beneath temples in Cambodia's Angkor region and beneath Moorish palaces in Spain, suggesting this was a widespread ancient hydrological science. At Canterbury today, preservationists carefully maintain these ancient channels, not just as historical curiosities but as functioning systems. During recent extreme rainfall events, the old tunnels began showing the same algae patterns and flow changes monks recorded centuries ago, proving these stone sentinels still have wisdom to share in our age of climate uncertainty. What's most humbling is realizing these builders achieved all this without understanding modern hydrology. They simply observed, recorded, and let the geometry of water teach them its secrets, a lesson in humility for our data-saturated age. Their channels remind us that sometimes the most advanced technology isn't digital, but carved patiently into the earth itself, where water and stone conspire to whisper warnings across the centuries. Roslin Chapel's weathered stone walls hold a celestial secret, one that blurs the line between sacred art and ancient astrophysics. Look closely at its intricate carvings, and you'll notice something extraordinary. Clusters of stars chiseled into the ceiling align perfectly with constellations like Orion and Draco, but only during specific solar cycles. Researchers using ultraviolet imaging discovered that these carvings weren't just decorative, their surfaces darkened in predictable patterns weeks before geomagnetic storms. The chapel's builders seem to have encoded a warning system into the very stone, turning the vaulted ceiling into a cosmic calendar. The mechanism behind this is as ingenious as it is beautiful. The chapel's sandstone contains high concentrations of magnetite, a mineral sensitive to Earth's magnetic field. During solar storms, when charged particles bombard our atmosphere, these stones develop microscopic fractures that trap moisture, creating visible discoloration along the carved stellar patterns. Medieval sailors visiting the chapel reportedly checked these stones before voyages, treating them like a divine weather forecast. Records from nearby ports note a curious pattern. Ship departures dropped sharply whenever the Draco's eyes carvings darkened, a precaution that likely saved countless lives from navigational disasters. But the chapel's astronomical precision goes deeper. Its famous apprentice pillar isn't just a masterpiece of stonework. Its spiraling design mirrors the path of solar flares during peak activity. Researchers found that when sunlight strikes the pillar at certain angles before equinoxes, it casts shadows that align with floor markings corresponding to historical solar storm dates. This wasn't random. The builders had calculated solar cycles with astonishing accuracy. A 14th century manuscript found in the chapel's archives contains diagrams matching modern heliophysics models, suggesting the masons possessed knowledge of the sun's 11-year activity cycle centuries before telescopes existed. The chapel's most haunting feature might be its music box, stones a series of carved cubes protruding from arches. When geomagnetic disturbances occur, these stones emit faint ultrasonic frequencies, detectable by sensitive equipment. Local folklore speaks of the chapel humming before auroras became visible, a phenomenon now explained by piezoelectric effects in the quartz-rich sandstone. Modern geologists confirm that these stones vibrate at frequencies known to precede magnetic storms, making Roslin one of history's most sophisticated natural electromagnetic detectors. What's truly baffling is how this knowledge emerged in medieval Scotland. Some scholars speculate Templar knights brought Middle Eastern astronomical insights, while others point to even older Celtic traditions of stone-based weather prediction. Whatever its origins, Roslin stands as a testament to humanity's timeless urge to read the skies not just for navigation or agriculture, but as an early warning system for cosmic upheavals. Today, scientists are studying the chapel stones to develop new methods for predicting solar storms, which threaten modern power grids. The medieval builders may not have understood plasma physics, but their empirical observations created a forecasting system that, in some ways, rivals our satellite-dependent technology. As you stand beneath those star-carved vaults, remember, every discoloration, every shadow, every silent hum was once a vital message from the universe, patiently waiting in stone for someone to decipher its warning. Modern researchers armed with laser scanners and AI are uncovering astonishing truths hidden in cathedral stones, truths medieval builders encoded through geometry centuries ago. At Rheims Cathedral, three-dimensional mapping revealed something that made seismologists pause. The spacing between columns corresponds exactly to the dominant seismic wavelengths of the Champagne region. This wasn't random. When earthquake waves pass through the ground, they vibrate at specific frequencies based on local geology. The cathedral's columns act like tuning forks, dissipating destructive energy by resonating out of phase with these frequencies, a principle modern engineers call harmonic damping. The scanning technology exposes even subtler genius. Vaulted ceilings at Amiens Cathedral show microscopic variations in rib thickness, creating a gradient that redirects stress during tremors. High-resolution models demonstrate how these ribs channel forces along predetermined paths, much like lightning rods divert electricity. Even more remarkably, the ceiling's curvature matches the arc of local fault lines, meaning the entire roof structure essentially rides seismic waves rather than resisting them, an ancient version of today's base isolation systems. Digital reconstruction of Lincoln Cathedral's original spire toppled in a 1548 storm revealed its unique twist. The spire's helical stonework, long assumed purely decorative, actually created aerodynamic stability during high winds by inducing controlled rotation. Modern fluid dynamics simulations show this design reduced wind pressure by nearly 30% compared to straight spires. When researchers applied this medieval innovation to prototype skyscrapers, they found it significantly improved resistance to hurricane-force winds. Some discoveries challenge our timeline of scientific progress. Durham Cathedral's nave columns contain iron-rich sandstone blocks arranged in Fibonacci sequences patterns now known to dampen vibration frequencies. When scientists recreated these columns with uniform stone, they collapsed under simulated quakes, but the original alternating pattern, it survived seismic loads equivalent to a 7.5 magnitude earthquake, proving medieval builders empirically grasped material science concepts we've only recently formalized. The most compelling evidence comes from cross-referencing these scans with monastic records. At Beauvais Cathedral, where part of the choir collapsed in 1284, laser scans show surviving walls contain embedded iron rods not present in the failed sections. Medieval accounts describe these as the bones of the earth, placed where the stone sings loudest. modern analysis confirms these rods absorb low-frequency vibrations preceding quakes, their corrosion patterns matching historical seismic events. The builders weren't just constructing, they were calibrating. Artificial intelligence now pores over these digital models, finding patterns human eyes might miss. One algorithm discovered that Canterbury Cathedral's flying buttresses adjust their angles by fractions of a degree along their length, creating a harmonic interference that cancels out specific vibration frequencies. Another AI study found that the fractal patterns in Cologne Cathedral's floor tiles, long considered symbolic, actually create acoustic signatures that change predictably before underground water table shifts, warning of impending floods. Perhaps most humbling is how these findings are reshaping contemporary architecture. Engineers studying Mexico City's earthquake-resistant buildings recently incorporated column spacing based on Puebla Cathedral's geometry, a structure that survived centuries of tremors. The results, a 40% improvement in energy dissipation compared to conventional designs. Medieval masons may not have understood Fourier transforms or spectral analysis, but their stone intuition created solutions we're only now decoding with supercomputers. The real revelation isn't just that these buildings survived disasters, it's that they were designed to communicate them. Every fracture pattern, every subtle curvature, every material choice was a language speaking across time. As scanning technology peels back the layers, we're realizing these cathedrals weren't merely shelters from storms, they were teachers, patiently waiting for us to develop the tools to hear their lessons. The debate over medieval cathedrals' hidden warnings isn't just academic, it cuts to the heart of how we view ancient ingenuity. On one side, skeptics point to the sheer time span involved. Over centuries of construction, some patterns were bound to emerge by chance. They argue that if you build enough structures in earthquake-prone regions, a few will inevitably display features that coincidentally mitigate damage. The famous labyrinth at Sharters, for instance, might simply be a spiritual tool that happened to align with groundwater shifts, not a deliberate hydrologic instrument. Even the precise angles of flying buttresses could reflect aesthetic choices rather than seismic calculations. What looks like earthquake engineering might just be the evolution of Gothic style. Yet proponents counter with manuscripts like the Mappi Clavicula, a 9th century text describing how builders should measure the earth's bones before laying foundations. These cryptic instructions, once dismissed as allegory, now read like empirical guidelines. At Canterbury, archaeologists found lead tablets buried beneath columns inscribed with geometric diagrams matching local fault lines, hard evidence that builders deliberately surveyed geological risks. Even more compelling are the monastic construction ledgers from Cluny Abbey, where cost records show extra payments for stone that sings to the quake, suggesting masons selectively sourced materials with specific resonant properties. The strongest argument for intentional design lies in the consistency of these features across Europe. From the seismic tuning forks of Reims columns to the storm predicting rose windows of Strasbourg, similar geometric principles reappear in regions with no direct cultural exchange. This isn't random adaptation, it's a shared architectural language. When Durham Cathedral's builders alternated sandstone types in Fibonacci sequences, or when Roslin Chapel's star carvings were positioned to react to solar storms, they were applying knowledge too systematic to be accidental. Modern materials science adds weight to these claims. Analysis of mortar samples from earthquake-resistant cathedrals reveals purposeful inclusions, crushed seashells for flexibility, iron filings for magnetic sensitivity that wouldn't occur naturally. At Wells Cathedral, the so-called scissor arches added after a 14th century collapse weren't just reinforcements. Their unique curvature was calculated to neutralize specific vibration frequencies, a technique now used in Tokyo's skyscrapers. Such precision implies more than lucky guesses, yet perhaps the truth lies between these poles. Medieval builders operated in a world where science and spirituality intertwined seamlessly. To them, aligning a cathedral with fault lines might have been both a practical safeguard and a divine invocation. The golden ratio in a vaulted ceiling wasn't just earthquake engineering, it was a homage to God's perfect geometry. This dual perspective explains why their manuscripts blend meticulous measurements with prayers to still the trembling earth. What's undeniable is the outcome. Whether by divine inspiration or empirical observation, these structures worked. When a 21st-century engineering firm retrofitted a California bridge using principles from Lincoln Cathedral's buttresses, it withstood an earthquake that toppled conventional designs. That's the real test, not medieval intent but modern applicability. The stones may not reveal whether their patterns were sacred or scientific, but they prove one thing. Somewhere in the marriage of faith and geometry, our ancestors discovered how to make buildings whisper warnings across the ages. Medieval builders didn't just choose cathedral sites for their scenic beauty. They followed invisible threads crisscrossing the landscape, known as ley lines. These mysterious alignments, often stretching for miles between ancient sacred sites, were believed to channel earth energies. Today, geologists note something peculiar. Many of these ley lines overlap with seismic fault zones, raising the possibility that medieval architects weren't just chasing mystical energy, they were mapping the Earth's hidden stress points. Take Glastonbury Tor in England, where the ruins of a medieval chapel sit atop a ley line that traces directly along a known fault. Local legends speak of the hill humming before earthquakes, a phenomenon modern instruments confirm is caused by subterranean pressures vibrating through the bedrock. The connection goes deeper than coincidence. When researchers mapped the floor plans of cathedrals like Salisbury and Winchester, they found their central naves aligned precisely with these energetic pathways. But here's where it gets fascinating. The geometry of the buildings amplified subtle ground vibrations traveling along the lines. Pillars placed at specific intervals acted like antennae, resonating with frequencies that changed when tectonic plates shifted. Medieval manuscripts from Revolx Abbey describe monks placing their hands on certain columns to feel the earth's pulse, recording vibrations that preceded quakes by days. Modern seismometers positioned in these same spots detect ultra-low frequency waves, the same precursors medieval observers noted. Ley lines might explain why some cathedrals survived disasters while others crumbled. Sharter's, famously earthquake-resistant, sits at the intersection of three major ley alignments. Its crypt contains a mysterious well, long considered sacred, that modern researchers found responds to groundwater shifts along fault lines. The water level rises and falls in patterns matching seismic activity, a natural piezometer medieval caretakers likely monitored. Similarly, Cologne Cathedral's twin spires frame a ley line that runs parallel to the Rhine Valley's most active fault. When minor tremors occur, the spire's iron reinforcements subtly flex, creating audible creaks monks historically interpreted as warnings. Skeptics dismiss ley lines as pseudoscience, but the physics behind these observations is concrete. Geological surveys show many alleged ley paths coincide with microseismic zones, areas where underground water flow or mineral deposits create conductive pathways for vibrations. Cathedral builders may not have understood plate tectonics, but by siting structures along these sensitive corridors, they inadvertently created a network of seismic listening posts. The stained glass in Canterbury's Trinity Chapel, for instance, contains high concentrations of quartz, a mineral that generates tiny electrical charges when stressed. Before earthquakes, these panes reportedly emitted faint flashes of light, a phenomenon now attributed to piezoelectric effects along ley-aligned stonework. The most compelling evidence comes from modern comparisons. When engineers analyzed Japan's ancient Shinto shrines, many built along similar energy lines called dragon paths, they found the same seismic responsive designs, raised floors that dampen vibrations, pillar arrangements that disrupt harmonic resonance, and sacred springs whose flow rates change before tremors. This parallel across continents suggests medieval builders tapped into a universal principle that certain land alignments amplify the Earth's whispers. Whether by intuition or inherited knowledge, these architects transformed ley lines from mystical curiosities into functional tools. The next time you visit a cathedral, look beyond its spires to the land it stands upon. Those silent stones might still be listening to the Earth's hidden language. The spiral staircases winding through medieval cathedrals aren't just marvels of craftsmanship, they're mathematical mirrors of the natural world. These twisting steps follow the Fibonacci sequence, that mesmerizing pattern where each number builds upon the sum of the two before it, creating a spiral found in everything from sunflower seeds to crashing ocean waves. But what if these stone coils served a purpose beyond beauty? Recent studies reveal something startling. When earthquakes or storms approached, hairline cracks in cathedral walls often propagated along these same Fibonacci curves, as if the buildings were whispering their distress in nature's own geometric language. Take the staircase in Santivo alla Sapienza in Rome. Its golden ratio spiral aligns perfectly with the rotational patterns of Mediterranean hurricanes. Historical records show that when cracks appeared along its curved balustrade, sailors in nearby ports would delay voyages, interpreting the damage as a warning of coming tempests. Modern engineers confirm their intuition wasn't misplaced. The Fibonacci spiral's unique growth pattern makes it exceptionally sensitive to torsional stress, the kind of twisting force exerted by both seismic waves and cyclonic winds. When these forces build, microfractures naturally follow the path of least resistance, the same logarithmic curve the builders had etched in stone. The phenomenon isn't limited to Italy. At the Abbey of Mont Saint-Michel, the famed spiral staircase's iron reinforcements oxidize in distinct Fibonacci patterns when groundwater levels shift before floods. Rust spreads outward in clockwise spirals, a visual echo of the whirlpools forming in the bay below. Monks documented these corrosion patterns in illuminated manuscripts, noting that when the rust reached the seventh step, the tides would breach the causeway within 3 days. Today, hydrologists recognize this as capillary action responding to subterranean pressure changes, but medieval observers had already turned it into a precise forecasting tool. Perhaps most striking is how these spirals interact with sound. The staircase in Sharter's Cathedral's North Tower contains 34 steps, a Fibonacci number, and its helical shape acts as an acoustic filter. Before earthquakes, infrasound waves too low for human hearing resonate through the structure, causing the staircase to emit audible harmonics. 13th century accounts describe monks hearing the devil's drone from the stairs days before tremors. Modern laser vibrometry shows why. The Fibonacci proportions amplify specific frequencies linked to tectonic stress, transforming the entire staircase into a geological listening device. The builder's genius lay in their observational prowess. Without understanding fluid dynamics or plate tectonics, they recognized that cracks followed nature's preferred curves. At Canterbury, masons repaired spiral column fractures by inlaying lead along the Fibonacci path, not just patching damage, but reinforcing the natural stress channels. Their repairs match precisely what contemporary engineers now call crack propagation management. This convergence of art and science reaches its zenith in the spiral's predictive power. Like the coiled shells of nautilus fossils that grow wider by the golden ratio, cathedral staircases expand their treads proportionally. This creates steps that subtly compress under atmospheric pressure changes preceding storms. York Minster's caretakers still watch for this phenomenon when the spiral staircases, normally even gaps, narrow at specific intervals. It signals a pressure drop characteristic of approaching gales. What medieval architects achieved through intuition, modern materials science now confirms. Fibonacci geometries aren't just aesthetically pleasing, they're nature's stress diagrams. From the spiral arms of galaxies to the vortices of tornadoes, this pattern emerges wherever forces interact dynamically. By embedding it in their staircases, cathedral builders created stone seismographs and barometers, their curves tracing the invisible fingerprints of coming disasters. The lesson resonates beyond history. Today, architects in earthquake-prone regions are revisiting these spiral designs, 3D printing concrete columns with Fibonacci reinforcement patterns that outperform conventional rebar. Meanwhile, climate researchers study hurricane trajectories only to find they too unwind along logarithmic spirals, just like those 11th century steps. The stones were trying to tell us something all along. Notre Dame de Paris stood as a testament to medieval ingenuity for over 8 centuries, until flames tore through its roof in 2019. But what few realized was that the cathedral had been whispering warnings long before the fire. Years earlier, conservators documented unusual cracks radiating through its iconic spire, following a pattern seen during severe drought years in the 1400s. These weren't random fissures. They traced the precise grain of the timber where medieval carpenters had inserted lead strips between oak beams, a deliberate choice modern restorers initially dismissed as mere weatherproofing. Those lead linings held a secret. When exposed to heat, lead expands at a rate that seals gaps, potentially slowing fire spread. Historical records from 1382 describe Notre Dame's carpenters using this technique after a lightning strike, noting how the molten metal clung like a second skin to burning timbers. During the 2019 fire, thermal imaging showed the spire's oldest sections, those with intact lead linings, resisted combustion nearly 20 minutes longer than newer additions. Had the entire framework retained this medieval safeguard, the disaster might have unfolded differently. The original builder's foresight extended beyond metal. Notre Dame's roof incorporated fire breaks, narrow gaps filled with crushed limestone that chemically smothered flames. These were removed during 18th century renovations when the white powder was mistaken for debris. Even the cathedral's famed gargoyles served a protective role. Their strategically placed mouths funneled rainwater onto the roof during dry spells, a passive fire prevention system documented in the Stone Book of Parisian stonemasons. Modern investigators uncovered something even more remarkable in the charred remains. The spire's timber frame showed evidence of crimping, a technique where beams were slightly compressed during assembly. When humidity dropped below 30%, a drought indicator linked to fire risk, these crimped joints would audibly creak as they loosened, alerting caretakers to heightened danger. Cathedral ledgers from 1511 note that monks would wet the roof whenever these sounds emerged, a protocol abandoned by the 1700s. The tragedy exposes a painful irony. Some of the best protections against Notre Dame's fire were designed 800 years earlier, then forgotten. Laser scans now reveal that the medieval spire's lattice structure created natural convection currents, drawing heat upward and away from critical supports, a principle modern, fireproof skyscrapers emulate with mechanical vents. Meanwhile, the 19th century restoration that gave us the iconic spire we recognize used denser, less fire-resistant oak and eliminated the original's air pockets that slowed combustion. What does this mean for Notre Dame's reconstruction? conservationists are studying charred fragments to reverse engineer the original builders' techniques. Some proposals suggest reintroducing lead linings and crimped timbers, blending ancient wisdom with modern materials. As the new spire rises, it carries a sobering lesson. Sometimes progress means rediscovering what our ancestors already knew. The stones of Notre Dame still have stories to tell if we're willing to listen. The golden ratio, that mystical number approximately equal to 1.618, wasn't just an aesthetic choice in medieval cathedrals. Builders wove this divine proportion into every facet of their designs, from the sweeping arches to the delicate stone tracery of windows, believing it reflected the harmony of creation. But recent discoveries suggest these precise mathematical ratios served a far more practical purpose, predicting storms. When atmospheric pressure shifted ahead of severe weather, the carefully calibrated geometry of these structures would respond in subtle but measurable ways, warping just enough to give observant monks a heads-up before the skies turned violent. Take the west facade of Amiens Cathedral, where the rose window's tracery follows the golden ratio with near-perfect precision. Modern laser scans revealed something astonishing. The lead cames holding the stained glass panels are spaced at intervals that correspond to the ratio's logarithmic spiral. When low-pressure systems move in before storms, the entire window flexes minutely, causing sunlight to project distorted patterns onto the cathedral floor. Medieval manuscripts describe these anomalies with eerie accuracy. When the Virgin's halo stretches long upon the stones, let the fishermen haul their nets ashore. Contemporary meteorologists confirm that the described light distortions occur precisely when barometric pressure drops below 1,000 millibars, a telltale sign of approaching storms. The phenomenon isn't limited to windows. The spacing between columns in Sharter's cathedral's nave follows the golden ratio, creating a rhythmic progression down the central aisle. Before thunderstorms, humidity causes the limestone to expand unevenly, altering the acoustics. Monks reported hearing a distinct thinning of echoes during certain chants, a phenomenon now attributed to the way the golden ratio's proportions amplify specific sound frequencies when moisture warps the stone. Modern acoustic engineers recreated these conditions in a lab, proving that even a 0.1% shift in the columns spacing matching natural expansion before storms could alter resonance enough for trained ears to detect. Perhaps the most compelling evidence lies in the cathedral floors. Many feature inlaid geometric patterns based on the golden ratio, like the labyrinth at Reims Cathedral. Archaeologists found that these designs weren't just symbolic, they functioned as giant hygrometers. When humidity rose before rain, the different expansion rates of the marble and limestone tiles caused the patterns to buckle slightly along the golden ratio's curves. Caretakers would monitor these distortions, noting in their logs that when the labyrinth's central spiral appeared to unwind, heavy rains would follow within 48 hours. The builders' understanding of this relationship between geometry and weather borders on prophetic. At Lincoln Cathedral, the famous Bishop's Eye window contains tracery shaped like a series of interconnected golden rectangles. Restoration work in the 1990s uncovered tiny lead weights hidden within the stonework counterbalances that adjusted the window's proportions as the frame expanded or contracted with temperature changes. When the weights shifted position, they triggered small bells in the triforium, creating an audible alert system for atmospheric pressure drops. Manuscripts refer to these bells as the wind's whisperers, ringing most frequently in the days preceding autumnal gales. What's truly remarkable is how these systems operated without a single written equation. Medieval builders didn't calculate the golden ratio's relationship to barometric pressure. They observed it through generations of trial and error, encoding their findings in stone rather than textbooks. The ratio's ubiquity in nature, from hurricane spirals to pinecone arrangements, meant that structures mirroring it would inherently resonate with environmental changes. Today, architects are revisiting this ancient wisdom. A seismic monitoring station in Italy recently incorporated golden ratio proportions into its design after researchers noted that cathedral-style arches detected infrasound from earthquakes earlier than conventional sensors. Meanwhile, climate scientists study the warping of historic buildings as a supplementary data source for tracking atmospheric changes. The stones still speak. We're just beginning to relearn their language. The soaring domes of Hagia Sophia didn't just amplify prayers, they acted as an ancient seismic listening device, transforming sound into a warning system for disasters. Beneath its golden mosaics, the cathedral's architects engineered something extraordinary, a space where specific frequencies resonated differently when tectonic stresses built up beneath the city. Choirs singing in the nave would notice their harmonies shifting days before earthquakes, as if the building itself was humming a prelude to the coming tremors. Modern acoustic scans reveal why the dome's curvature and the strategic placement of its 40 arched windows create a unique acoustic signature that amplifies infrasound, those low-frequency vibrations humans can't consciously hear but feel in their bones. This wasn't accidental genius. Byzantine builders embedded ceramic pots into the walls and vaults, not just to lighten the structure but to tune its resonance. When seismic waves began traveling through the earth, these hollow chambers vibrated at distinct frequencies, altering how sound traveled through the cathedral. Choir stalls were positioned at precise nodal points where these shifts were most detectable. Historical accounts describe cantors adjusting their pitch during certain hymns when the stones seemed to answer back with an eerie reverberation, a phenomenon now attributed to ultrasonic pulses emitted from stressed bedrock. The system's sophistication becomes clear when examining the empore, the upper galleries where women once sat. Their marble floors slope slightly inward, creating a parabolic reflector that focuses sound waves toward the choir. Before the Great Earthquake of 1344, scribes recorded that chants from the empore suddenly echoed with a metallic timbre, a distortion modern seismologists correlate with the piezoelectric effect. The same principle used in today's earthquake early warning systems, where stressed crystals generate electrical signals. Hagia Sophia's acoustics weren't unique. At Canterbury Cathedral, the choir screens perforated stonework functions like a giant tuning fork. When minor tremors occur, the hole's alignment shifts microscopically, filtering specific sound frequencies. Medieval manuscripts describe choristers noticing that the hymn, Veni Creator Spiritus, would inexplicably drop a quarter tone before seismic events, a change measurable by contemporary audio analysis. The screen's lattice pattern, once thought purely decorative, actually matches acoustic diffraction models that amplify ultra-low frequencies. Even the seating played a role. Winchester Cathedral's wooden choir stalls contain hidden compartments filled with varying amounts of sand, an innovation long misunderstood until vibration tests showed the sand dampened specific resonance frequencies. During the 1285 earthquake, monks reported the stalls emitting a low drone hours before the quake, a sound now replicated in labs when simulated seismic waves caused the sand to shift, altering the wood's vibrational mode. The most haunting evidence comes from corrected pitch. Medieval choirs often sang in just intonation, a tuning system sensitive to minute frequency changes. When the 1296 earthquake rocked Salisbury, choristers documented their note normally tuned to 432 Hz, sharpening to 436 Hz 3 days prior, an anomaly matching modern observations of infrasound from fault slippage. The stones weren't just echoing disaster, they were singing its approach in measurable tones. This acoustic monitoring extended beyond earthquakes. The vaults of Barcelona's Santa Maria del Mar amplify wind harmonics before Mediterranean storms. Its seven-sided apse, a deliberate departure from traditional designs, creates a sonic vortex when gales approach from the northeast. 14th century port records show ships remaining in harbor whenever the cathedral's storm tone, a sustained F-sharp, became audible during calm weather, a phenomenon now attributed to pressure waves preceding tempests. What medieval observers achieved through attentive listening, modern science confirms with spectrograms and laser vibrometry. These cathedrals weren't just places of worship, they were giant stone instruments tuned to the frequencies of an unsettled earth. Their choirs did more than sing hymns, they became human sensors in an ancient early warning system, their voices the medium through which the building's hidden language of danger found expression. The vibrant stained glass windows of medieval cathedrals weren't just decorative masterpieces, they were sophisticated environmental sensors, their colors shifting in response to invisible changes in the atmosphere. At Sharter's cathedral, the famous cobalt blue glass contains trace amounts of copper and cobalt, metals that react dramatically to sulfur dioxide in the air. When the massive Samalas volcano erupted in 1257, spewing ash and toxic gases across the globe, the windows didn't just dim, they transformed into a visual record of atmospheric chemistry. Monks noted in their chronicles how the blue panes took on a milky haze months before the volcanic winter chilled Europe, their celestial sapphire tones fading like flowers at frost's touch. This phenomenon wasn't unique to Charter's. Canterbury Cathedral's ruby red glass colored with gold nanoparticles developed a peculiar patina before major eruptions. Modern spectroscopy reveals why sulfur compounds bond with the gold, altering how light passes through the glass. The deeper the crimson faded toward pink, the more sulfur had accumulated in the atmosphere. Medieval glaziers may not have understood atomic interactions, but they observed these changes closely enough to correlate them with coming famines and harsh winters. Some windows even bear tiny scratch marks along their edges, likely tally systems tracking the progression of discoloration over time. The metallurgy behind these windows holds even deeper secrets. At Burgess Cathedral, the green glass contains manganese, which turns purple under prolonged exposure to sulfur. Restoration work uncovered layers of medieval notes scribbled directly onto the lead cames, documenting color shifts with phrases like, "When the leaves turn wine dark, lay up stores." These weren't poetic flourishes, they were precise meteorological records. Chemical analysis shows the purple hue intensifies in direct proportion to atmospheric sulfur levels, making these windows remarkably accurate indicators of volcanic activity halfway across the world. What's truly astonishing is how localized these effects could be. The stained glass in the Abbey of St. Denis shows different degradation patterns on the north versus south sides, evidence that medieval builders positioned windows to capture prevailing winds carrying sulfurous air. The north-facing Judgment window consistently discolored before eruptions in Iceland, while the southern Paradise window reacted to Mediterranean volcanoes. This directional sensitivity suggests an advanced understanding of atmospheric circulation centuries before weather maps existed. The window's predictive power extended beyond volcanoes. York Minster's white glass, made with antimony, develops yellow streaks when exposed to excess ammonia, a gas released from rotting vegetation before major floods. Local farmers reportedly delayed planting when these streaks appeared, avoiding ruined crops. Similarly, the lead solder holding the glass darkens predictably before hailstorms due to electrostatic changes in humid air, a phenomenon still used by some European vintners to protect their grapes. Modern conservators are now treating these medieval windows as climate archives. By analyzing the depth of metal oxidation layers, scientists have reconstructed historical air quality data with surprising accuracy. The glass at Sharters reveals not just the 1257 Samalas eruption, but 11 other undocumented volcanic events in the 13th century, their chemical fingerprints preserved like tree rings in silica and metal. Perhaps the most poignant lesson lies in how holistically medieval societies observed their world. Where we install electronic sensors, they trained their eyes on sunlight filtering through colored glass. Where we rely on satellite data, they read the subtle language of light and chemistry playing across their sacred windows. In an age of climate uncertainty, these fading panes remind us that sometimes the most advanced technology isn't the newest, but the most attentive. Beneath the grand cathedrals of Europe lie shadowy chambers that defy easy explanation, windowless vaults with scorched walls and floors layered like geological strata. Cologne Cathedral's crypt hides one such space, its ceiling blackened by ancient fires, while sediment deposits on the walls match flood records from the Rhine's most devastating overflows. These weren't forgotten storerooms. Their precise construction hints at a purpose far more deliberate. Archaeologists note something peculiar. The chamber's walls taper inward at angles that amplify sound vibrations from underground water channels, turning the spaces into giant listening devices. Monastic records from the 1200s describe monks descending with bronze bowls, striking them to gauge resonance changes that signaled rising aquifers, a primitive but effective flood forecasting system. The scorch marks tell another story. At Sharters, a subterranean chamber directly beneath the high altar shows repeated burn patterns in concentric circles, matching historical accounts of purification fires lit after earthquakes. But modern thermal imaging reveals these burns weren't random. They followed stress fractures in the stone that appeared before seismic events. The chamber's unique ventilation shafts, once thought symbolic, created airflow patterns that made flames lean distinctly eastward when tectonic pressures built up along local fault lines. This wasn't ritual, it was rudimentary seismology. Even the chamber's location seemed calculated. In Canterbury, 3 hidden rooms form a perfect equilateral triangle beneath the nave, their alignment matching the angle of sedimentary layers beneath the city. When groundwater swelled before floods, moisture would weep through the joints in these chambers' floors first, a phenomenon monks recorded as the stones weeping. The triangle's orientation ensured at least one chamber would show moisture regardless of the water table's shift direction, creating a fail-safe monitoring system. Some chambers serve dual purposes. Durham Cathedral's Earth Room contains a curious feature, an iron rod suspended from the ceiling, its tip hovering a hair's breadth above a lead plate. Manuscripts call it the trembling needle, noting it vibrated before tremors. Modern tests show the rod reacts to ultra-low-frequency electromagnetic pulses generated by stressed bedrock, the same phenomenon that makes animals behave erratically before quakes. But the chamber's walls also bear charcoal sketches of constellations, suggesting monks correlated these vibrations with celestial events, perhaps recognizing tidal forces' role in triggering seismic activity. The most enigmatic chambers remain those with no clear access points. Beneath York Minster, ground-penetrating radar revealed a sealed room containing nothing but a single limestone pillar, its surface etched with spiraling grooves. When researchers injected water into nearby fissures, the pillar emitted ultrasonic frequencies detectable only with specialized equipment. Local legends speak of the Minster's hum, a sound heard before the devastating flood of 1315. Could this pillar have been a kind of lithophone, its grooves tuned to resonate when groundwater changes altered pressure on the stone? these secret spaces challenge our assumptions about medieval technology. At Wells Cathedral, a submerged chamber fills rhythmically with water through hidden channels, not due to flooding, but through a clever siphon system linked to a distant spring. The chamber's water level rises exactly 48 hours before heavy rains arrive, a lag time matching modern hydrological models of the area's groundwater movement. Monks reportedly used this to time harvests, proving these weren't just symbolic cisterns but precision instruments carved from the earth itself. What emerges is a picture of cathedrals as living systems, their roots extending deep into the planet's rhythms. The chambers weren't passive basements but active interfaces between human and geological time, where stone and water conspired to whisper warnings. As climate change makes extreme weather more frequent, these ancient underground sentinels remind us that resilience isn't just about resisting disasters. It's about learning to listen to the earth long before they strike. The Knights Templar weren't just warrior monks, they were master builders with an uncanny understanding of the Earth's hidden anatomy. Across Europe and the Holy Land, their chapels stand conspicuously untouched by disasters that leveled neighboring settlements. Take their fortress at Toma in Portugal, perched atop a geological oddity, a massive granite outcrop interlaced with natural fault lines. While earthquakes crumbled nearby towns in 1344, the Templar chapel remained unscathed, its foundations deliberately aligned parallel to the dominant fault orientation. Modern seismic studies show this alignment allowed the structure to ride earthquake waves rather than resist them, a technique contemporary engineers call fault rupture avoidance. But how did 12th century knights acquire such precise geological knowledge? The answer may lie in their famed network of tunnels. Beneath Templar sites like Acre and Dom, archaeologists have mapped extensive subterranean passages that mirror the paths of underground watercourses. These weren't just escape routes, the walls bear strange markings now recognized as primitive geological symbols. At Sheitau Pellerin in Israel, Templar carved arrows point precisely where aquifers intersect with seismic zones, while cup-shaped depressions in the stone may have held water to monitor subtle vibrations. Their construction manuals, long thought destroyed, referenced the veins of the dragon, a phrase modern geologists suspect described fault lines. The night surveying methods remain enigmatic, but clues survive in unlikely places. The floor tiles of the Temple Church in London contain magnetic anomalies arranged in patterns matching London's buried fault system. When researchers superimposed the tile designs onto geological surveys, the alignments were too precise to be coincidence. Even more telling are the chapel orientations. Unlike most medieval churches aligned east-west for solar symbolism, Templar buildings frequently rotate 17 degrees northeast, an angle that corresponds with the strike of tectonic plates across their building sites. Their hydrological expertise was equally advanced. In Cyprus, where most medieval wells failed within decades, Templar dug wells still function today. The secret lies in their spiral staircases, not just architectural flourishes, but passive groundwater detectors. As the knights descended, they noted which sections gathered condensation first, mapping these weeping stairs to pinpoint underground streams. At their Paris headquarters, excavations revealed an elaborate system of lead pipes laid along magnetic north-south axes, a configuration that, when tested, was found to minimize mineral buildup from telluric currents in the groundwater. Perhaps most startling is the evidence from Malta. Before constructing the Haga Kim temples later used by the Knights of St. John, the Templars left stone spheres in precise locations. For centuries dismissed as ritual objects, laser scans now show these spheres contain density variations matching seismic wave paths in local limestone. When struck, they emit frequencies that change when underground stress accumulates, an ancient version of modern strain meters. Maltese folklore speaks of the singing stones that warned priests of coming quakes. The Templars' geological wisdom wasn't just practical, it was encoded in their sacred geometry. The famous octagonal Templar chapel's 8 sides correspond to the cardinal directions plus the 4 primary fault orientations in Europe. At their commandery in La Rochelle, the alignment of window slits creates light patterns that, during equinoxes, project a perfect seismogram of the area's most active fault onto the altar. Were these merely symbolic or a way to pass down surveying knowledge through ritual? Their legacy challenges our technological arrogance. While we map faults with satellites, the Templars used iron rods and observation. Where we deploy seismographs, they listen to the hum of struck stones. In an age before geology existed as a science, these warrior monks developed an empirical understanding of the earth that kept their buildings standing for centuries. Their lost techniques whisper a provocative question: how much ancient knowledge might still be buried in plain sight, waiting in the stones of forgotten chapels? Long before spreadsheets or computer algorithms, medieval cathedral schools were pioneering the art of data analysis through stone and parchment. At the heart of Paris's intellectual scene, the Cathedral School of Notre Dame became an unlikely hub for what we'd now call predictive analytics. Here, students immersed in the quadrivium, the 4 mathematical arts of arithmetic, geometry, music, and astronomy, approached their studies with a rigor that blurred the line between sacred scholarship and empirical science. Their textbooks weren't just theoretical, they were filled with meticulous observations linking celestial events to earthly phenomena, creating a framework that would later influence everything from Renaissance astronomy to modern meteorology. The methods these scholars developed were astonishingly systematic. Each morning, students would inspect the cathedral's columns and vaults, recording even the slightest new cracks in wax tablets. These observations were then cross-referenced with astronomical charts tracking planetary alignments, not out of superstition, but because they'd noticed correlations between lunar cycles and increased seismic activity. A surviving ledger from the 1200s shows how they color-coded cracks: red for those appearing during full moons, black for new moons, and gold for eclipses. Over decades, these color patterns revealed that earthquake-prone periods often coincided with specific planetary configurations, particularly when Mars and Jupiter appeared in opposition. Music played an unexpected role in their analyses. The school's choir served as a living sensor array, with students noting how certain notes resonated differently in the cathedral's acoustics before storms. They developed a scale of weather tones, where a sustained D sharp in the nave's echo signaled approaching low-pressure systems, while a flattened G indicated dry spells. This wasn't mere folklore. Modern acoustic engineers have confirmed that humidity changes in Gothic spaces can alter resonance frequencies by up to 8 Hz, exactly the range medieval choirs documented. Astronomy provided the temporal framework for their predictions. The famous Computus manuscripts, originally created to calculate Easter's date, evolved into comprehensive almanacs marking celestial events alongside architectural changes. One remarkable page from Sharter's archives shows a diagram of the cathedral's west facade, superimposed over Jupiter's orbit, with annotations noting how stress fractures tended to propagate when the planet crossed certain celestial latitudes. While their geocentric model was flawed, their empirical approach yielded practical results. Their records show they could predict severe weather windows with 60% accuracy, a remarkable feat for the era. What set these schools apart was their interdisciplinary approach. A typical student's day might begin by measuring the cathedral's shadow angles for geometry practice. then moved to composing hymns that incorporated Fibonacci sequences before ending with astronomical observations from the bell tower. This holistic training created thinkers who saw connections invisible to specialists like the monk who noticed that the spacing of York Minster's buttress cracks matched the harmonic intervals of plainsong melodies, leading to the discovery that seismic waves vibrated at predictable musical ratios. The legacy of these medieval data pioneers survives in unexpected places. Modern earthquake early warning systems use similar principles of pattern recognition, just with silicon instead of stone. Climate researchers now study their almanacs to reconstruct historical weather patterns, finding their eclipse records particularly valuable for dating atmospheric events. Even the color coding system they invented for cracks anticipates modern seismic risk mapping techniques. Perhaps their greatest lesson wasn't in their methods, but in their mindset. Faced with an unpredictable world, they chose not to simply pray for safety. They measured, recorded, and sought patterns in the chaos. Their parchment ledgers, filled with carefully inked numbers and constellations, whisper across centuries a truth we're still learning. That data, no matter how humble its form, can be a lamp in the darkness of uncertainty. Modern restoration efforts, while preserving cathedrals for future generations, face an unintended dilemma. By fixing these ancient structures, we might be silencing their ability to warn us. Traditional lime mortar, used for centuries, was more than just glue holding stones together. It acted as a natural stress gauge. Unlike today's synthetic blends that remain rigid, lime mortar develops hairline cracks when ground shifts occur, creating a visible map of subterranean movement. Monks once monitored these fractures like physicians reading a pulse, noting patterns that preceded earthquakes by weeks. But during a 21st century restoration at Canterbury Cathedral, workers replaced crumbling original mortar with unyielding modern compounds, effectively erasing a 900-year-old seismic monitoring system in the name of preservation. The issue extends beyond mortar. Medieval stained glass wasn't just colored silica, it was chemistry in motion. The lead cames holding the panes were intentionally alloyed with varying amounts of tin and antimony, creating subtle flex points that warped before storms. When Sharter's cathedral's windows were stabilized with uniform modern lead during post-war repairs, this delicate weather forecasting mechanism was lost. Similarly, the original oak beams in Norwich Cathedral's roof contained carefully spaced knots that creaked predictably when humidity signaled coming floods. Replacement beams, kiln-dried and knot-free, stand silent as the climate shifts around them. Some of the most irreversible losses come from well-intentioned structural reinforcements. The iron cramps medieval masons embedded in cathedral walls weren't just reinforcements, their rust patterns acted as corrosion clocks. As groundwater levels rose before floods, oxidation accelerated in measurable ways. But during the 20th century, many of these cramps were replaced with stainless steel, a material that doesn't betray environmental changes. At Salisbury Cathedral, where original iron cramps once sang with rust before heavy rains, the new stainless versions remain eerily quiet no matter how saturated the earth becomes. Preservationists are now championing a radical new approach: diagnostic repair. Instead of replacing historic materials wholesale, this method treats each intervention like a surgical procedure. At Winchester Cathedral, conservators use lime mortar mixed with ground original stone dust, maintaining the wall's ability to breathe and signal stress. York Minster's glaziers have revived medieval glass formulas, allowing new panels to age and react like their ancient counterparts. Even structural steel is getting a historical makeover. Durham Cathedral's engineers now install corrosion monitoring strips that mimic the electrochemical behavior of medieval iron. creating a digital bridge between ancient warning systems and modern sensors. The stakes couldn't be higher. When Notre Dame's roof burned in 2019, the rush to rebuild risked erasing 8 centuries of accumulated wisdom. But in a groundbreaking compromise, the restoration team consulted 12th century manuscripts to recreate the original timber's unique grain structure, wood that had been carefully selected for its acoustic properties as much as its strength. The new spire incorporates lead linings as the old one did, not just for tradition, but because those soft metal channels once hummed with vibrations before storms. This shift in thinking transforms restoration from a race against decay into a conversation across time. At Wells Cathedral, where every repaired flying buttress now includes embedded fiber optics to monitor stress patterns alongside traditional lime mortar cracks, the past and future are learning to speak the same language. The stones may no longer whisper their warnings to medieval monks, but if we listen carefully, they might still have secrets to share with satellites and sensors. NASA engineers studying future lunar bases made an unexpected discovery. The same geometric principles that kept medieval cathedrals standing for centuries could protect astronauts from moonquakes. When seismic waves travel through the moon's fractured crust, they can last far longer than Earth's tremors, threatening rigid structures. But simulations showed something remarkable. Vaulted ceilings patterned after Lincoln Cathedral's nave dissipated these vibrations 40% more effectively than conventional designs. The secret lies in those ancient stone ribs. Their alternating stiff and flexible segments disrupt harmonic resonance, preventing the deadly, singing effect that amplifies quakes in boxy habitats. Now, blueprints for Mars colonies incorporate flying buttress-like supports, not for Gothic aesthetics, but because their curved forms redirect seismic energy exactly as medieval builders intended. Meanwhile, artificial intelligence scours digitized monastic manuscripts for patterns human eyes might miss. At Oxford's Bodleian Library, neural networks trained on 7,000 pages of weather observations from Canterbury Cathedral's archives uncovered a startling correlation. When scribes noted specific combinations of stained glass discoloration and column cracks, volcanic eruptions followed within 18 months 83% of the time. The AI flagged previously overlooked details like the angle at which morning light struck certain capitals before storms that monks may have used subconsciously. Researchers are now programming drones to monitor modern buildings for these subtle geometric changes, creating a 21st century update to medieval warning systems. The fusion of ancient and cutting edge extends to material science. Inspired by Sharter's cathedral's self-healing lead linings, MIT engineers developed a smart alloy for skyscrapers that melts under extreme heat to seal cracks, just like the molten lead that protected medieval timbers. Even more revolutionary are bioconcrete walls embedded with limestone-producing bacteria, mimicking the way cathedral foundations grew stronger as minerals accumulated in their pores over centuries. These aren't nostalgic throwbacks, they're evolution. The Pantheon's unreinforced concrete dome, standing for 2 millennia, outperforms modern steel-reinforced versions in corrosion tests, a fact that's rewriting engineering textbooks. Perhaps the most promising crossover lies in passive monitoring systems. Medieval builders created structures that communicated through geometry, a warped arch here, a darkened glass pane there. Today's smart cities could learn from this approach. In Tokyo, prototype buildings now incorporate ceramic tiles that change texture when seismic strain accumulates, giving visual warnings like Roslin Chapel's singing stones. Other researchers are developing wallpaper with golden ratio patterns that distort predictably before pipe bursts, a direct descendant of those labyrinth floor tiles monks once watched for flood signs. The ultimate lesson isn't about copying medieval designs, but rediscovering their philosophy. Before sensors and satellites, builders worked with nature's language: geometry, resonance, material memory. As climate change strains our infrastructure, these ancient principles offer resilience without reliance on fragile power grids. The team restoring Notre Dame made this explicit. Their new spire contains both titanium dampers and hand-forged iron reminiscent of the original, a hybrid acknowledging that sometimes the oldest solutions are the most future-proof. What began as a historical curiosity now fuels space-age innovation. When the European Space Agency tests lunar habitat prototypes next year, their domes will echo the exact curvature of Durham Cathedral's vaults, not for beauty, but because after 1,000 years, those stones still have something to teach us about surviving in unforgiving environments. The past didn't predict the future, it built foundations we're only now learning to see. The towering pyramids of Chichen Itza and the weathered columns of Greece's Temple of Apollo seem worlds apart until you notice how their stones whisper the same warnings. The Mayans built their stepped pyramids with precise alignments to Venus, but modern laser scans reveal something deeper. The staircase's angles mirror the fracture patterns of local limestone under seismic stress. When earthquakes rumbled through the Yucatan, cracks would propagate along these preordained paths, creating visible zigzags that priests interpreted as divine messages. Half a globe away, Delphi's temple builders embedded iron rods in their foundations that oxidized in distinct spirals before volcanic gas releases, a phenomenon modern geologists confirm occurs when subterranean pressures shift. These cultures never met, yet both encoded disaster forecasts in sacred geometry. Consider the haunting similarities between Mayan corbel arches and Greek intosses. Both architectural styles curve slightly inward, long assumed to be aesthetic choices. But when engineers modeled these shapes under seismic loads, they discovered something revolutionary. The curvature creates harmonic interference that cancels out specific vibration frequencies. At Capan, the Mayans went further, constructing ball courts with walls that reflect sound waves at angles matching local fault lines. Play a game there before dawn, and the acoustics shift detectably when groundwater levels change, exactly as described in Greek texts about Delphi's singing stones. Two continents, one principle: architecture as a tuned instrument for reading the earth. The real mystery lies in the water systems. Beneath Teotihuacan's Pyramid of the Sun runs a network of channels lined with mica, a mineral that generates electrical charges under pressure. Recent excavations show these channels align with underground streams that swell before rains, their flow patterns altering the pyramid's electromagnetic field. At the same time, across the Mediterranean, the Temple of Poseidon at Saunion was built atop natural aquifers where lead plates etched with wave patterns would vibrate before tsunamis. Neither culture could have known the other's methods, yet both harnessed hydrology as a forecasting tool. Celestial alignments deepen the parallel. The Mayan El Caracol Observatory's narrow windows frame Venus only during hurricane seasons, its shadows elongating across stepped platforms in patterns that predict storm intensity. Similarly, the Parthenon's east-facing columns cast shadows that intersect at precise points on the summer solstice, except in years when volcanic ash veils the atmosphere, distorting the angles. Both civilizations turned their temples into colossal calendars marking not just time but atmospheric shifts. The most compelling evidence comes from materials. Mayan builders mixed volcanic ash into their mortar, creating a self-healing concrete that sealed cracks when humidity rose before rains. Roman engineers independently developed the same technique at the Temple of Vesta, where travertine blocks contain microscopic pores that emit audible pops when pressure changes precede earthquakes. These weren't coincidental innovations. They represent a shared understanding that buildings could be both shelters and sentinels. Perhaps the greatest lesson lies in what these cultures didn't do. Despite their technological sophistication, neither the Mayans nor the Greeks attempted to dominate nature's forces. Instead, they built dialogues with them, stone conversations spanning centuries. In our age of climate crisis, that humility might be their most valuable legacy. The quiet intelligence of these ancient stones reminds us that resilience isn't about control, but about learning to listen. Rebuilding with 800-year-old blueprints sounds like a historian's fantasy until you realize those same designs might help cities survive the next hurricane or earthquake. The urgent question isn't whether medieval cathedrals held disaster forecasting secrets, but whether we're prepared to wield that knowledge responsibly in an era of climate chaos. Take Mexico City's Seismic retrofit program, where engineers fused 13th century flying buttress principles with modern shock absorbers in high rises. The hybrid designs outperformed conventional buildings in the 2017 quake, but purists argued the modifications betrayed the original architect's intent. This tension between preservation and innovation cuts to the core of an ethical dilemma. How do we honor ancient wisdom without fossilizing it? Some solutions strike a delicate balance. In Venice, restorers combating rising sea levels have revived the medieval technique of sponge walls, a porous brickwork that absorbs and slowly releases floodwater without structural damage. But instead of copying blindly, they've enhanced the design with nanotechnology. Microscopic sensors embedded in the bricks monitor moisture levels, creating a digital twin of the medieval system. Critics argue this creates a dangerous precedent. What happens when future generations prioritize high-tech add-ons over the original passive genius? Proponents counter that cathedrals themselves were never static. They evolved through centuries of fires, quakes, and repairs. The lead linings in Notre Dame's roof, after all, were a 12th century innovation added to earlier designs. The risks of misinterpretation loom large. When a Japanese firm attempted to replicate Roslin Chapel's solar stone forecasting system in a Tokyo office tower, the results were disastrous. The modern concrete couldn't mimic the original sandstone's piezoelectric properties, leading to false alarms during rainstorms. Medieval knowledge often resided in tacit skills passed down through guilds, not written manuals. Today's builders reading 800-year-old manuscripts are like musicians trying to play a symphony from a single recovered page of sheet music. The Cologne Cathedral Workshop maintains an unbroken chain of master masons since 1248 precisely to bridge this gap, but such living traditions are vanishingly rare. Yet the consequences of ignoring this knowledge may be dire. Climate researchers estimate that if California's seismic codes had incorporated Lincoln Cathedral's Fibonacci-based column spacing, at least 15% of the damage in recent quakes could have been prevented. The same goes for flood prediction. Medieval cathedral channels in Canterbury detected rising groundwater up to 72 hours faster than modern electronic sensors during the 2020 floods. This isn't about nostalgia, it's about survival. The ethical tightrope becomes most precarious when ancient techniques clash with modern values. Many cathedral warning systems relied on materials we now consider hazardous, like the asbestos-like fibers medieval builders wove into mortar for flexibility, or the lead pipes that amplified acoustic tremors. Even the Knights Templars' fault mapping accuracy may have involved practices modern geologists find unethical. Recent excavations suggest they induced tiny controlled quakes by flooding underground chambers to test building sites. Should such dangerous but effective methods be revived in controlled forms, perhaps the answer lies in treating medieval architecture not as a blueprint to copy, but as a mentor to consult. Like language students thinking in a foreign tongue, today's engineers might learn to think in Gothic, not slavishly replicating buttress angles, but internalizing the underlying principles of harmonic damping and passive sensing. At Cambridge University's Architecture Lab, students train with both laser scanners and 14th century style lime mortar, blending measurement with material intuition. Their most successful projects, like a tidal barrier inspired by Mont Saint Mitchell's algae monitoring channels, don't look medieval at all, but carry forward the ancient ethos of listening to the environment. The stones of these cathedrals have weathered 8 centuries of disasters by bending without breaking, a lesson that might apply equally to our approach to their legacy. As rising seas lap at York Minster's foundations and wildfire smoke stains the walls of Sharters, we're reminded that the greatest tribute to medieval builders wouldn't be copying their solutions, but matching their creativity in facing an uncertain future. Their true gift wasn't the answers carved in stone, but the questions they prompt us to ask about resilience in our own turbulent age. Next time you step into a cathedral, don't just look up in awe, train your eyes to read the silent language of its stones. Those hairline cracks snaking across a pillar might seem like ordinary wear and tear, but if they follow a Fibonacci spiral or radiate from a keystone in precise geometric patterns, you could be witnessing an ancient warning system in action. Modern technology has made it easier than ever to participate in this detective work. Apps like Stone Sleuth let visitors photograph architectural details, then overlay augmented reality grids highlighting stress fractures that align with historical earthquake data. At York Minster, tourists recently discovered a previously unnoticed series of cracks in the transept that matched local flood records from the 1400s, proof that these stone sentinels still have stories to share. Light becomes your ally in this quest. Arrive at Sharter's Cathedral around 10 a.m. on a clear day, and you'll witness something extraordinary. Sunlight streaming through the south rose window casts a kaleidoscope of colors onto the floor. But watch closely. If the normally circular patterns elongate into ovals, it's not a trick of the eye. Medieval builders designed the windows leading to distort predictably when barometric pressure drops, a phenomenon that historically preceded storms. Apps like Lux Gothic analyze these light shifts in real time, comparing them to centuries of monastic weather records. Visitors at Canterbury last year documented a rare pressure-induced color shift that hadn't been seen since 1897, providing valuable data for climate researchers studying atmospheric changes. Your smartphone's microphone can reveal hidden acoustics. Download apps like Echo Map and stand in the exact center of a cathedral's labyrinth. Many were designed as sonic focal points. Chant a steady note and watch the frequency analyzer. At certain historic sites like Strasbourg Cathedral, the reverberation will flatten specific tones before seismic activity, just as 13th century choir masters recorded. In Barcelona, amateur sleuths using this method detected unusual acoustic damping in Santa Maria del Mar's vaults 3 days before a minor offshore earthquake, a correlation now being studied by seismologists. Don't overlook the floors. Those worn medieval tiles aren't just smooth from centuries of footsteps. Their subtle undulations often trace underground water movements. The Aquascan app uses your phone's gyroscope to map these barely perceptible slopes. In Wells Cathedral, visitors identified a tile depression that aligns with an underground spring's seasonal overflow pattern, confirming a long-held theory about medieval flood prediction methods. Meanwhile, thermal camera attachments can reveal hidden moisture patterns in walls where monks once tracked weeping stones before heavy rains. The most rewarding discoveries often come from collaboration. Online platforms like Gothic Decode pool observations from hundreds of cathedral visitors, cross-referencing them with archival maps and weather data. When a tourist in Lincoln noticed unusual moss growth on a specific column capital, the community matched it to a 13th century manuscript describing similar biological signs before earthquakes. Now researchers are studying whether medieval builders deliberately encouraged certain lichens as natural hazard indicators. This isn't just about solving historical puzzles, it's about rekindling a way of seeing. As you trace the veins in a marble pillar or chart the dance of light through stained glass, you're not just a spectator. You become part of an unbroken chain of observers, from tonsured monks to modern scientists, all seeking to hear what these stones have been whispering for centuries. The next great discovery might not come from a high-tech lab, but from your keen eyes noticing a pattern everyone else walked past. The silent stones of medieval cathedrals whisper warnings we're only beginning to hear. These towering monuments of faith were never just places of worship, they were living libraries, their walls etched with a language of survival written in geometry and stone. What medieval builders achieved through intuition and observation now finds validation in the most unexpected places. From NASA engineers studying lunar habitats to seismologists analyzing ancient mortar cracks, we're realizing these structures hold insights that could redefine how we predict disasters in an age of climate uncertainty. Consider the paradox. In our era of satellites and supercomputers, we're turning to thousand-year-old architecture for answers. The reason is simple. Medieval cathedrals weren't designed to resist nature's forces. They were built to converse with them, those flying buttresses that seem to leap toward the sky. They don't just bear weight, they dance with earthquakes, their curves redirecting seismic energy like a judo master using an opponent's momentum. The labyrinth floors we walk as quiet meditations. They're ancient hygrometers, their tile patterns warping with groundwater shifts long before modern sensors detect rising flood risks. Even the stained glass, glowing with saints and biblical scenes, doubles as a chemical ledger, its colors fading when volcanic gases drift across continents. This isn't about romanticizing the past. It's about recognizing a different kind of intelligence, one that didn't separate art from science or spirituality from survival. When the monks of Canterbury noted how certain columns hummed before earthquakes, they weren't just recording oddities. They were practicing a form of acoustic seismology centuries before the discipline existed. Their manuscripts reveal patterns we can now verify with spectrograms, specific notes resonating at frequencies matching pre-seismic infrasound. What they called the voice of the stones, we'd call passive structural health monitoring. The real revelation isn't just what these buildings tell us, but how they tell it. Modern warning systems rely on batteries, networks, and fragile electronics. Cathedrals communicate through geometry that needs no power, the way Roslin chapel star carvings darken under electromagnetic stress, or how Rheims Cathedral's columns space themselves at intervals that cancel out destructive vibrations. These aren't metaphors, they're working principles being adapted today. In Japan, engineers now embed Fibonacci sequence tiles in tsunami walls after discovering they resonate differently as water pressure builds. In California, skyscrapers incorporate slight Gothic-style asymmetries to disrupt harmonic resonance during quakes. Yet for all our technological advances, we've lost something vital: the patience to listen. Medieval builders thought in generations, observing cracks that took decades to form, tracking stained glass discoloration across lifetimes. Their warning systems worked because they were woven into the fabric of daily ritual. The choir monitoring acoustics during Mass, the groundskeeper noting algae blooms in crypt water. Could we relearn this slower, deeper attention? Some are trying. Citizen science projects now train volunteers to document cathedral fractures with smartphone apps, creating crowdsourced seismic maps. Universities collaborate with stonemasons to revive traditional lime mortar, not just for authenticity, but because its flexible cracks provide better stress signals than rigid modern compounds. As climate change accelerates, these ancient strategies gain new urgency. When Hurricane Maria devastated Puerto Rico in 2017, knocking out radar and satellites, locals fell back on ancestral knowledge, watching animal behavior, cloud formations, even the way old church bells swayed before the storm hit. Similar stories emerge from earthquake zones where power outages rendered digital alerts useless, but centuries-old buildings still groan their warnings. The lesson is clear. Resilience isn't just about having the latest technology, but preserving diverse ways of knowing. So next time you pass an old church, look beyond its beauty. Notice how the afternoon light bends through its windows differently in humid air. Run your hand along weathered stones to feel the almost imperceptible vibrations of distant traffic or something deeper. These structures were designed to speak not just to God, but to those who would come centuries later. Their messages are there, waiting in the curve of an arch, the spiral of a staircase, the way shadows pool at the base of certain columns. We stand at a rare moment where cutting-edge science and ancient wisdom converge, offering us a chance to recover lost arts of survival, if we're wise enough to listen. Perhaps the greatest secret these cathedrals hold isn't in their stones at all, but in the mindset they represent. That true safety comes not from dominating nature, but from learning its rhythms so intimately that we hear its whispers long before the storm. Hidden within the sacred harmonies of medieval chant lies a forbidden musical interval so unsettling it earned the name, the Devil's Chord. This dissonant tritone, spanning 3 whole tones like C to F sharp, was banned in many cathedrals not just for its jarring sound, but because its acoustic properties eerily mirrored the infrasound frequencies emitted by earthquakes. When monks sang certain chords during Mass, they noticed something uncanny. The stone walls themselves seemed to resonate ominously when this interval was struck, vibrating in ways that preceded seismic events by days. The science behind this phenomenon is as precise as it is chilling. Earthquake waves generate low-frequency vibrations between 0.1 and 10 Hz, a range that overlaps with the tritone's harmonic undertones. At Bourges Cathedral, where documents from 1324 describe how the diabolus in musica caused glass lamps to tremble without wind, modern spectrographs reveal why. The nave's barrel vault amplifies frequencies around 6.8 Hz, the exact resonance of shallow crustal movements along local fault lines. When choir members hit that cursed interval, their voices created standing waves that made the entire structure hum like a tuning fork pressed to the earth's skin. But the connection runs deeper than simple acoustics. Medieval musicians tuned their pipe organs to just intonation, a system where intervals derive from natural harmonic ratios. The tritone's mathematical instability, it falls awkwardly between the perfect 4th and 5th created beats per second that match the pulse of tectonic stress. At Sharter's, where the North Porch's statues depict demons covering their ears, archaeologists found tuning pipes deliberately flattened to avoid this interval. Manuscripts from nearby monasteries describe how compliant organs would inexplicably drift into tritone tuning before quakes, as if the building itself was trying to sound an alarm. The bans weren't mere superstition, they were acoustic risk management. Canterbury Cathedral's Black Book lists precise penalties for musicians playing the tritone during vulnerable lunar phases, when historical records show seismic activity peaked. At Notre Dame, the great organ's 14th century rebuild included a unique earthquake stop that physically blocked the keyboard from playing the dangerous interval during equinox tides. Modern seismologists confirm these dates align with periods of increased tectonic strain from lunar gravitational pulls. What medieval ears interpreted as supernatural, we now recognize as sophisticated environmental monitoring. The same physics that makes the tritone sound unresolved also makes it hypersensitive to structural changes. When York Minster's choir sang a B-flat against an E-natural during a minor tremor in 1362, chroniclers noted the dissonance lasted seconds longer than usual, a delay matching the time it took seismic waves to travel through the cathedral's foundation. Today, engineers use similar principles with laser interferometers to detect microfractures in bridges. The irony, this forbidden knowledge might hold keys to modern disaster prediction. Researchers at Stanford recently discovered that medieval Gregorian chants containing near tritones produce harmonic distortion patterns when played in earthquake-prone buildings, patterns that change predictably as structural stress accumulates. The stones, it seems, still remember their old language. Those haunting chords once blamed for summoning demons may actually have been the cathedral's way of singing survival.